Hello. Sorry for coming late. Yes, so maybe we can talk now about maybe key means clustering, for example. But maybe just a quick introduction to principal component analysis. We'll talk about principal component analysis before. We use it for dimensionality reduction, in fact, and it's unsupervised as well. So principal component, it's unsupervised because we try to focus on reducing number of features or number of dimension of our data set. So so we try to get rid of non-relevant or not so relevant features and keep as much as of interesting ones as possible using the principal component. Dimensionality reduction allows AI to be more efficient in solving larger scale and computationally expensive problems. So for example, if we have images, videos, text, speech, and so on, we try to reduce number of dimensions to make the problem more simple, for example, for our AI algorithm. Principal component identifies which features out of a full set of features are most important in explaining variability in the data set and filter out features that are less useful in exploring the data set. So we can, okay. We talk also about key means clustering here. So key means clustering, it's we specify number of desired cluster. So it's unsupervised. So we need the user, in fact, to define number of clusters because we don't know anything about data. So you have a data set, for example, you have iris data sets. So we have 4 features. And if we will use key means clustering, we need the algorithm to understand how many clusters do we want, how many clusters. So we need to get some knowledge from a domain expert. So the domain expert should say, okay, our data set has 3 clusters or 4 clusters. So the algorithm can try to classify it or cluster it into this number of clusters. To speed up clustering process, key means randomly assign each observation to one of the key clusters and then begin to reassign these observations to minimize the clean distance between each observation and its cluster center point or centroid. So different of key means, each with randomized start will result in slightly different clustering assignment of the observation. From those different runs, we can choose the one which has the best separation, defined as the lowest total sum of within cluster variations across all clusters. So in fact, key means the cluster, we run it different times, and each time we have different assignment of data points to clusters. So each time we should get different results, in fact, and we should select the one with lowest cluster variations. So we need to get clusters which are very compact. So we need to select the most compacted clusters because each time we will get different results. But the idea here is to get which looks like very compacted, very close to each other. So so this is key means clustering. We can use also key means from sklearn.cluster. So we can import it from sklearn.cluster key means. And of course, in key means clustering, it's recommended to normalize all features, right? Because if we didn't normalize, maybe some features will have huge impact because we calculate Euclidean distance, right? We calculate Euclidean distance. So imagine that we have 2 features, one in kilometer, one in millimeter, for example, and we're calculating Euclidean distance. So in this case, maybe the clustering will be biased against some features. So it's important to normalize your data points. So all data points are between 0 and 1, for example. So when we calculate the Euclidean distance, it shouldn't be biased. So first,
only normalization, no standardization, or both.
It could be both, but we need to test it. We need to test it, but at least because we calculate Euclidean distance. So Euclidean distance, if you have one feature in 10 millions, another features in millisecond, for example, so it will be a problem in calculating Euclidean distance. So it's important to have all your features normalized between 0 and 1. So we can have some fair way for calculating this Euclidean distance.
How many clusters should be?
What?
How many clusters we need?
You need to select, you need to choose. User should say how many clusters, right? So for example, Ali, you are working in a data set, and I mean, you visualized it, and when you're looking into it, you feel, okay, this one looks like 3 clusters. So for example, if we can look into Iris data set. No, I want to get just a graph. This one, it's Iris data set. It looks like this one, it's clearly, this is 1 cluster. Maybe this one, we can have here maybe 3 clusters or 2 in that part. Maybe this one will be 1 cluster. Maybe this one could be 1. Maybe we can have here another cluster here, right? So it could be 4. But when we talk to the domain expert who knows Iris dataset very well, he will say, no, it's only 3 clusters. So please just select 3, because we have knowledge from the domain expert. Because after clustering it, we need to give a label to each cluster, right? So we have 3 clusters. So we need to say, okay, this is cluster number 1, this is cluster number 2, this one will be number 3. We need to give it a label after solving the problem. So how this one works? I mean, usually, I mean, we select 3 cluster centers or centroids by random, right? And we start calculating the distance. So for example, I will start with the first one. So I have some data points here, and I selected. We want to get 3 clusters. So k equals 3, for example, right? So I will select 3 centroids by random. So imagine that this one, it's the first centroid or center. I will calculate the Euclidean distance between this one and the neighbor point. So this is the neighbor 1. I will calculate the Euclidean distance. So I will realize that this one, it's the closest to the centroid here, right? And after that, I will update the centroid by taking the average between the centroid and the new point, which is closer to it. So in this case, I will make it one more time here. This one is centroid. Those are data points, right? So I selected the centroid as a data point by random. So we selected k clusters, so we will select the 3 points by random as the centroids. So second, I will calculate the distance between the centroid and all data points, and I will sort in ascending order or descending or ascending order, and I will select the closest one. So maybe the closest one will be this one, right? It looks like this one. So we will calculate the Euclidean distance, and I will select the one which is closest. Maybe this one, it's the closest. I will update the centroid by taking the average between this point and the centroid. So the centroid will move to that place here. It will be here. This one will be the new centroid. But remember, this one was data point. After that, I will calculate the Euclidean distance with the rest of the data points. Maybe this one was closest, so we will update the centroid to be here in that location, and so on until there is no change. In fact, we will repeat this process several times until there is no change. And at the end, I will have a centroid for each cluster. This one will be the centroid for this cluster. This one will be the centroid for this cluster. This one will be the centroid of this cluster. And after training the algorithm, in fact, here it's parametric model, because we will have some parameters. We will have the centroids. After training my k-means clustering, for k equals 3, we will have 3 centroids. So we will have C1, C2, C3, and that is it. So after training your k-means clustering, you will have 3 center points, 1 for each cluster. And when you have a new data point, imagine that we got new data point here. So how can we classify it? I will calculate the Euclidean distance between this new point and the 3 centroids, right? And I will assign it to the one which is closest to it. So this one looks closer to green, so this one will be green, will be classified as green. So k-means clustering, and after training a k-means clustering, we will have 3 centroids or k centroids. Those centroids will be the centers of the cluster. And if you have a new data point or new example and which you want to classify, you will calculate the Euclidean distance between the new data point and the 3 centroids, and it will be assigned to the one. It will be given the label of the closest cluster or centroid. So first, I selected 2 and 3, or maybe 3 and 4 features. I did min-max normalization. I split the data into, training and testing, because I want to test the accuracy of the algorithm in the testing data set, for example. But remember, it's unsupervised. So we are not using, so when we trained the model, look, we selected k equals 3. This is maximum number of iterations. So we will repeat this process 1,200 times. And each time we will calculate within variation of the cluster. And we will pick the one with less variation, because each time you will get different results. So each time you will have 1,200 times solutions, for example, right? We need to pick the one which is best for us. How can we measure it? By calculating within cluster variations. So we calculate within cluster variations for all those solutions, and we will select the one which has less within cluster variation. So the cluster looks like more compacted. So when we train the model, we will train it with X-train. Do you see this one? Only X-train, because it's unsupervised. So we are not considering labels here at all. We are just using features. So we use X-train for training, and those are the centroids. If you want to print out the centroids, you can just print those centroids and use X-test for prediction. Now we have Y-predict, but for this X-test, we have Y-test. So you can, even if you want to plot a confusion matrix, or if you want to calculate prediction accuracy, you can do it. But in general, we don't do this in fact, right? Because we don't have labels. In reality, we don't have any labels. We don't measure performance. But here, I just do it because we want to know what is the difference between supervised and super. But in reality, we don't have any labels. But I used the labels here to calculate accuracy using this accuracy score, right? So we use this one for calculating the accuracy, or even if you want to plot confusion matrix, you can plot the confusion matrix. So, so the accuracy will be 91% at the end, but it's unsupervised, right? This one, it's unsupervised. So we have almost the same accuracy as KNN. I mean, in KNN, we got maybe 93% accuracy. This one, it's unsupervised, and we got accuracy equal 91%. The advantage here, after training your algorithm, you will have the centroids. And in this prediction function, if you want to classify an example, you calculate the Euclidean distance between this example and the 3 centroids. And it will be given the label of the closest centroid. That is it. So this algorithm is very, very simple one. And it's not memory demanding. And we have training, because after training, you will get those 3 centroids. So at the end, you will have 3 centroids, C1, C2, C3. And if you have new example you want to classify, you will just calculate the Euclidean distance between this example and C1, C2, and C3. And it will be given the label of the closest centroid, and that is it. So it's the same here. When we are plotting, we did the same also as we did last time. So we have here a centroid. We have here a centroid. We have here a centroid. So maybe it also looks strange, but we need to plot this graph in equal axis. If we can plot it in equal axis, maybe it will be much better than this. Because as also, as you can see here, we have some data points here. It looks like closer here, and the longer distance from this one should be assigned to the yellow cluster. But because I'm plotting in the default approach, maybe we need to plot this one in equal axis to have better view of. It will look better. But remember, the accuracy it's 93%, which means we have 7% of the data points are misclassified, right? So we have 7% misclassified. So some confusion here. Sometimes we have some flower which should be green, but it's not green, and it has been classified as yellow, for example. So maybe you have some problems here, some confusion, right? And it's the same when you have dogs and the cats. Sometimes you have dogs and the cats who are equal, maybe size. So people can get confused between is it cat or is it a dog, for example. If it is very, very small dog, maybe people can just say, okay, no, it looks like a cat. So it's this kind of confusion. It's okay because human can be confused. And if we can be confused, it should be possible also for the algorithm to be confused. So this one, it's unsupervised, and in this unsupervised, we used only x1 and x2. We didn't use labels. It will be classified into 3 clusters. The algorithm will not understand what C1 mean, what C2 mean, what C3 mean. In fact, it will just be a cluster. So we need someone to go and annotate it. It will just say, okay, this one it's a Setosa, this one it's a versicolor, and so on, right? So if it is cats and dogs, the algorithm will classify it into maybe something here and something here. But we need a human, in fact, to go into the data and say, okay, this one it's a dog, this one it's cat. We need someone to annotate it, in fact. So now we will have a centroid for this one and centroid for this one. And if we have a new image, for example, we will calculate a clearance distance from each centroid, and it will be given the label of the closest one, and so on. Yes. So just remember that k-means clustering. It means this maximum number of iterations. We run the algorithm 1,200 times, for example. So we will get 1,200 times solutions or centroids. Which one we will select? We will select the one with the less within cluster variations. This one. We will calculate maybe variation within the cluster, and we will select the one with the less variation. So it looks like more compacted. It looks like very nice compacted. Yes. Any question for this k-means clustering? So just to try to run an example, go to Iris dataset, for example, and try to run it in 4-dimensional space, for example. We do it here for 2-dimensional space because I want to plot it in 2-dimensional space. You can make it in 4-dimensional space. And see, is there any difference in accuracy? Maybe the accuracy will be better because we will have more information. I mean, the accuracy here is 91% because, in fact, I'm using only 2 features, not 3, not 4. Maybe if you can try 3 and 4, maybe you can get better accuracy. Because it's better length, width, and simple width and length. So maybe if we will have the 4 features, we can get maybe 99% accuracy. Yes. Any questions for this k-means clustering? So if you have your data set now, and can you try to use k-means clustering, a KNN algorithm, try, because it would be nice. Try to build this pipeline, which we did last time, and try to use this pipeline to try different algorithms with different hyperparameters. I mean, maybe the only hyperparameter here, maybe it's distance. How we measure distance, for example. Is it Euclidean distance? Is it Manhattan distance? So, I mean, number of clusters, it's based on the domain expert, based on the data. When you plot the data, it looks like 3 clusters, so we will go for 3 clusters. But maybe for some other problems, you can go for 4, 5. For example, you have customers, you don't know preference of customers. You need to cluster them. You can just make them at 10 categories, for example, or 8 categories, 5 categories. Yes. Autoencoder also it's unsupervised, and we use autoencoder also for dimensionality reduction, in fact. And the autoencoder, it consists of 2 sections or 2 parts. It's symmetric, feed-forward neural network. So this one, in fact, it's feed-forward neural network, and it's symmetric, and it consists of two parts. The first part, it's encoder. The second part, it's decoder. So for the encoder, the input, it's the original image, and we try to convert this original image into a code or compress the form of the image. And after that, the input to the decoder will be this compressed representation of the image or the code, and the output will be the reconstructed image. So in fact, maybe just imagine that the input here will be cat, image of a cat, for example, and the output will be an image of a cat, correct? It's a reconstructed image, it's not the original image. So we have here the original image, the output here will be reconstructed image, the same number of pixels. So if this one is 28 times 28 pixels, the output also should be 28 times 28 pixels. This code, you need to decide it by yourself, how much compression you want to do, for example. So this one, it's 28 times 28, maybe this one should be 9, right? 9 pixels. So now, so do you see how much compression? So I compress an image from 28 times 28 pixels into, for example, you can just make it 9 times 9, 9 times 9 pixels. So it will be compression more than maybe 95% compression. You can just divide 9 times 9 divided by 28 times 28 times 100%. So how much percentage? You can see the compression, how much compression we are doing if we will do it like this. So yeah, so it's 10%, right? Which means we are making the compression by 90%. We try to compress the data by 90%, right? So the autoencoder is very, very important, very, very important. So we use it for compression to compress the data, and it consists of 3 components: encoder, code, and the decoder. The encoder compresses the input and produces the code. The decoder reconstructs the input only using the code. Autoencoder learns new representation of the original input data by the encoder to minimize reconstruction error between newly reconstructed data and the original input. So we will reconstruct the image here. We will subtract, in fact, this image from the original image to get something we call it reconstruction error. And the optimization algorithm will train the autoencoder in a way to minimize this reconstruction error. So you can just, for example, you can put your image here and initialize the weights with random values. You will get some random image here. And with iterations, the autoencoder will be able to reconstruct the same image as the input here, right? Because we subtract the reconstructed image from the original image. So at the beginning, the reconstruction error will be very large value. And after training, iteration by iteration, this reconstruction error will decrease, and reconstructed image will be identical to the input image. After training, we will have a code here. We will be able that this code will be good representation of this input image or good reduction. So the code here will be something useful which can be used to reconstruct the original image. So after that, we will take the first part, which is the encoder, and we will use it for dimensionality reduction. So after training the autoencoder and after being happy with the reconstruction errors, as the reconstruction error become very, very small, we will split it into 2 parts, and we will use the first part, which is the encoder for dimensionality reduction. So all images which are coming from a sensor, from a camera, it will be compressed into a code, and this code will be given to maybe a feed-forward neural network or a deep neural network, which can make some decisions. We use this one because instead of working with the original image, which may be high definition, so the model will be very complex, maybe the model will overfit, but we can reduce it from this size into this small size and build a very simple model. So the model will not go for overfitting, for example. So it's a way to simplify, neural network models to avoid being overfit. For example, if you want to make a joke, for example, or a play, for example, you can, for example, imagine that you want to encrypt a message or an image. You want to send it to a friend abroad, for example. So both of you can train autoencoder. And in one side, you will use a autoencoder for generating the code here in Norway, for example. You will send him the code by email. He will get the code, and he will use a decoder for reconstructing the image one more time. Just imagine it. It's intelligence. How do you call it? It's a work of like intelligence, right? So you will have an image. You will compress it into a code. You will send the code to someone else, and he will use the decoder for generating or reconstructing the image using the code. So we can use it for dimensionality reduction, because now we are reducing the dimension of the data from 28 times 28 into 9 times 9. So it's a dimensionality reduction. Number of pixels has been reduced from 28 times 28 into 81, which means we reduced the number of dimensions by 90%. We compressed the image by 90%, in fact, right? So in this case, instead of working with the original size, or with the original dimension, we will work only with the code. And in this case, we will guarantee that when you build a model, this model will be very simple and it will not overfit your data set. So we use it for compression and we use it for dimensionality reduction. So this is an example. I used it to, but you have, Maria, you have a question about Keras. So this one from Keras, I used the Keras here for building the autoencoder. So I built the autoencoder for Iris. So I will use a sequential API from Keras. Using this sequential, you can build any feed-forward neural network, deep learning or feed-forward, whatever. So we just use this sequential API, and after that, you will add some layers. So the first layer, for example, it will consist of 32 units. The activation function will be linear, and the dimension of the input will be 784. 784, it's 28 times 28. And you can give it a label, for example. I can call it encoder layer, for example. So in this case, the number of units here, it's the code size. In fact, this is the code. So if I want to plot this one, it will be like this one. In the middle here, we have the code 1, 2, 32. And the input layer, we will have the encoder. It will be like this one. But this one, it will be 1, 2, 3, 4 until 784. And after that, we will create the decoder. So the decoder will be the same size. It will be 1, 2 until 784. So the first part here, we call it encoder. And the second part here, it will be the decoder. So it's symmetric. So how many layers we have? How many? We have input layer, we have this hidden layer, we have output layer, and it's symmetric. So now if we will train this one, we will reduce the image size from 784 pixels into 32 pixels, right? So the first part, it's encoder. The second part, it's decoder. We will build it like this one. So we use the sequential API. We have 2 layers. So the first layer has this is the number of inputs. This is the number of units, right? And we call it encoder layer. And the decoder layer, it will be the same, but number of inputs will be 784. Number of outputs, number of units. This is the number of outputs. And the number of inputs, we don't need to specify it. It will inherit it. It will get it automatically from the previous layer. So the number of input here will be 32. So we have 2 layers. We just have 2 layers. It's symmetric, right? So the encoder layer and the decoder layer. Number of inputs of the decoder, it will be 784. Number of outputs will be 32. For the decoder, number of inputs will be 32. Number of outputs will be 784. So it's symmetric. When you have also this nice, so you use sequential API from Keras. You define the first layer, the second layer. You give it a name, encoder, decoder layer, and after that you need to select your optimizer. you need to select also the object cost function. I use the mean squared error. I use the mean squared error here, in fact, because we calculate the distance in pixel-wise, the distance between each two pixels. So we calculate mean squared error between pixels, pixel values, because I need to minimize the error between reconstructed image and the original image. After that, you can plot the model. So when you have this autoencoder.summary, you will get information here. You will get this table. And when you use the command plot model, you will get this picture here. So it will describe all things. In this table, for example, we have two layers. We have encoder layer, we have decoder layer. So this is the output shape. So the output shape will be 32 outputs from the first layer. The second layer, the number of outputs will be 784. Can you calculate this number of parameters? Can you calculate this number? Mattia, can you find?
I can try. Just give me a second.
Okay.
So it would be 32 times 784, right?
Yeah, correct.
Plus 7. No.
Plus bias. How many bias we have? How many units we have in this
32
layer?
bias.
32, right?
Yeah, 32. This is very good. Okay, what about the second one?
Same thing, but now we have 784 biases instead of 32.
Yeah, this is correct. This is correct. Yeah. So here is the encoder. Number of inputs will be 784. Number of encoder. This is the input layer. So just as this one do nothing in fact, but this one it's 784 inputs, 32 outputs. For the decoder layer, we have 32 inputs and 784 outputs. So this one will be like this. So after that, we need to train the autoencoder. We will train it using X-train, Y-train, number of epochs. You need to define maybe batch size, for example. And the validation maybe, because we need to validate. So here, I use the X-train, but remember here, the input equal X-train, and the output equal X-train. Did you notice this? So in fact, it's feed-forward the neural network, and we use error backpropagation. So it's in fact, in reality, it's unsupervised. It's supervised, correct? It's supervised technically, in fact, but in reality, because we train it using X-train, the input will be X-train and the output will be X-train, so we call it unsupervised, because we don't use any labels. So we don't care if the image is cat or dog. We just, the input will be an image and the output will be the same image. The label will be the image, the input image. So the input will be X-train and the output will be also X-train. For validation, the input will be X-train, the output will be, it should be X-test, sorry, this one should be X-test. And this one will be X-test as well, right? Not X-train. Because here I'm just using the testing set as a validation set. So this one should be changed into X-test and X-test. So the input will be an image, the output also, or the label will be an image. And the reconstruction error will be the difference between the target image and the output. So we can get the reconstruction error. We will train it iteration by iteration until this reconstruction error becomes very, very small.
Sorry, when we are done with training the model, what part do we use? Do we just use the code in production? Or okay.
After training the autoencoder, you will split it, and you will use only the first layer, this one. You will use only this layer, because we need to use it for dimensionality reduction, right? We need to use it for data compression. So the one which compress, it's the first layer. So we will just use, after training it, we will split this one into we will just pick onto this layer, and we'll use this layer for compressing my data points, because after training, this layer alone, which is the encoder, it will be able to compress the data from its original size into 32 bits or 32 pixels. So this is the error, loss, and accuracy for training and maybe training and validation. So this is an example. We used this MNIST dataset, right? So each image here, in fact, it's a 28 times 28 pixels. And I used it for, I trained this model already, and after that I will pick the encoder. I will pick only this layer, the encoder layer. So the encoder layer, it's layer number 0, correct? So this model here, we have this model which is called the autoencoder. This autoencoder has 2 layers, layer 0, layer 1. If you will use layer 0, which means the encoder, layer 1, it's the decoder. So if you want to pick only one, if you want to split it, you need to get only layer number 0. So now I used the layer number 0 in a model. I created a new model using this layer, and I will use this one for compressing my data points. So I used I defined a new model. And the input to this model will be the input to the autoencoder, and the output will be the output from layer 0 or layer 1, right? Which is the autoencoder layer. So now this one will be used for data compression. This one will be used for data compression. Because when you are using this one now, what will happen? The input will be the autoencoder input, which is 28 times 28, and the output will be 32 values. So now we can use this one for data compression. So if I have this encoder, I can use it for prediction. So the input will be an image, and the output will be encoded image, which is the code. This one, it's encoded image or the code. So the size of this one will be the original size, and the size of the output will be the code, which is 32 bits. 32 bits here, I put it 8 times 4 times 8, right? 4 times 8 pixels, because I want to plot it in this way. So this one, it's 4 times 8. So now the input image, it's 28 times 28, and the output will be 4. This is the code, which is representing this one. It's compressed representation of the original image. If you want to reconstruct the image using this code, you will get this image. So you can define another model. We can call it the decoder. So the input to this one will be the encoded input, right? It will be the encoded input, this one, and or the encoded input or encoded image, for example, and the output will be the output from last layer. This one means it's last layer, right? So the input will be the encoded input, and the output will be this decoded image. So this is the decoded image. So this one, it's original. This one, this is the code. This one, it's decoded or reconstructed image. Did you see? The quality, it's not the same, because when you compress and reconstruct, we will lose some information, of course. So now, as I told you, if you want to make a game, you can just train an autoencoder, use it for compress some pictures, for example, send it to a friend, and send him to the code in another email, for example, and he should store it in a safe place, and he can use this one for reconstructed the image using this code. It can work also for text. It can work for any other types of datasets. Yes. So now instead of working with the original image, I can build a model to classify according to the code, right? Because now the model will be simple. So I can just use feedforward the neural network, and instead of working with the original image, which is 28 times 28, no, I can just use with the code. So the model will be simple, and when the model is simple, you can just imagine how much reduction in the model. So imagine that we have one hidden layer, and this hidden layer has 100 units. And if you will use the code, so how many parameters we have here? It will be 32 times 100 plus 100, right? But if you will use the original, so it will be 784 times 100 plus 100. So in fact, we reduced the model complexity maybe by more than 90% or 95%, if you can make those calculations. So when we reduce model complexity, we reduce model capacity, and when we reduce model capacity, chances to overfit will be very, very slim. And now we don't need too much data, in fact, because when the model is complex, you need much bigger data set to train your model. And then when you have much bigger data, you need computational resources, you need memory, you need a GPU. So all things will be more complex. The idea from using autoencoder, you have here one layer, you can attach this layer to the model itself, in fact, directly, and freeze it. So when you train your model, you don't need to retrain the encoder again. So the idea here, I can plot. You have a model for classifying. Yeah, so you have a model here. Maybe this model will classify those numbers into digits from 0 to 9. So the input here will be the code. So you can just get the encoder, because I know the encoder, I trained the encoder already, and it will generate this code. So I can just attach it to my model here. This one, it's the encoder. You can attach it to the feed-forward neural network, which will classify those digits into numbers, right? But freeze. Remember to freeze those weights. So when you retrain the model one more time, you don't destroy the weights which has been trained already, right? So you can just attach this one here as one layer. This encoder will be here, layer number 1, for example. Layer number 2 will be this one, layer 2, layer 3, layer 4, for example. But remember to freeze the weights of the encoder. So when you retrain the whole model again, you don't damage the weights which has been trained, because we trained the auto encoder already before. And after training it, and after being happy with the performance, you can split it into encoder and decoder, and you can use the encoder as the first layer of your feed-forward neural network for decision making. If you are using principal component analysis, you cannot do it. You cannot combine it together. You need to apply PCA into your data points, get some reduced set of features, for example, using it for training your model. But the idea from using autoencoder here, you can combine it with your model, stick it all together, because it will be just one layer, input layer. But remember, this input layer, we don't need to retrain it again, so we need to freeze the weights. I mean, because I don't want it to be retrained again. When I need to retrain the whole model, I will just adjust those weights here, but not the encoder. Yes. If you want to go deeply, it's fine. So if you want to build a deep autoencoder, but just remember, just add more layers, but just remember that it's symmetric. This is the most important. So I can make it 6 layers, for example. So the first 3 layers will be the encoder, and the last 3 layers will be the decoder. So when it's deep, it means we have more hidden layers. Just remember, it must be symmetric. It must be symmetric. So last time we used only two layers. Now it's 6 layers, right? So we will convert first from 784 into 128, and after that from 128 into 46, from 46 onto, from 64 into 32. So this is the encoder part. And after that, we will start increasing again in the same way, from 32 to 64, from 64 to 128, from 128 to 784. So it's symmetric. So when it's deep autoencoder, it means we just try to add more hidden layers. So this is how we build it in Keras, Maria, because you have asking about this So just use Keras. Keras, very, very simple one. So we just need to define using this sequential API. You can give it a name, autoencoder equals sequential. We import sequential from Keras. So if you go into this code, you will see that we import sequential from Keras. So you add layer by layer. So the first layer will be converting from this input dimension into this dimension. The second will be converting from this dimension to this dimension. The third will be from this dimension into this dimension. So this one, it's the encoder part. After that, we will add the same number of layers for the decoder. So the decoder, we will go in the reverse direction, in fact. So we will go from 32 into 64, and from 64 into 128, from 128 into 784. So the dimension of the input is the same as the dimension of the output, because we can subtract pixel by pixel and calculate the reconstruction error. And here we use error backpropagation for training those weights. And we will train it, select optimizer, select loss function, metrics, and you can also generate the summary. You can have the plot from your model. And after that, you will train your model using xtrain, right? Remember, because it's unsupervised. So the input is xtrain, the output is xtrain, the same. Sorry, I did a mistake here. This one should be xtest, ytest. Sorry, xtest. This one should be xtest for validation, for example. So now this is the performance of the deep autoencoder. Also, if you want to, I want to split it into encoder and decoder, right? So it's the same. You need to define a new model. Maybe you can call it encoder, for example. The input will be the input to the autoencoder. The output will be the output from layer number. Which number? We have 6 layers. So this is the autoencoder. We have 6 layers. 1, 2, 3, 4, 5, 6. So this is layer 0, 1, 2, 3, 4, 5. So we have here the autoencoder part. So if you want to get the output from layer number 2, it means this is the code which we want to get. So here I've selected, you need to get the output from layer 2, because this is the one in the middle, in fact, which generates the code. And you will use this one for encoding. We use this one for encoding, for converting from original image into the code, and therefore we call it encoder. If you want to the decoder, the other part will be the decoder. So here, I mean the decoder, it will be also the output will be decoder layer number 3, right? This one, -1, it means it's the last one, in fact. This one means it's the last layer, this one. Or we can call it -1 or number 5. It will be the same. So this is the original image. This is the code. This is the reconstructed image. You see also that, I mean, it's not the same contrast, not the same resolution, but because we are compressing the data, we compress the data, but we compress it, and we are still able to identify it, right? So still we know that this is 1, 4, this one looks like 0 or 6, this one 1, this one looks like 9, right? But also if we compress the data, in fact, there will be a cost. We will lose some accuracy, right? But it's accepted because we understand it, because we compressed our data. When we compress the data, we will make the model more simpler, more easy to deal with, at the cost of losing some resolution, for example. Yes. Here I try to, here in fact, we used linear activation function. Do you see here? We used the linear activation function. When I change activation function into ReLU, we got much better results. Do you see? I mean, the accuracy much better. It's almost identical when we used ReLU. And I can understand, because the pixel values, maybe the pixel values, it's not numbers between 0 and 1, right? I don't know. In this image, I need to check it, in fact. I mean, each pixel value here, it's number between 0 and 255. So maybe if you can normalize it and use linear activation function, you will get better results. But if you don't want to normalize, in this case, you need to use ReLU, because ReLU will take care of large values. So if you want to use linear function or Gaussian function or whatever, you need to divide each pixel value by 255. So if we divide this one by 255, each pixel value will be converted into number between 0 and 1. In this case, we can use maybe linear function, Gaussian function, hyperbolic function. But if you don't want, if you want to use the numbers as it is, in this case, we need to use ReLU. Because ReLU's activation function will be like this one, right? So it will take care of all values between 0 and infinity, in fact. And since each pixel value is a number between 0 and 255, so ReLU will perform better with my autoencoder. And you can see it here. Do you see? It's almost the same. Almost the same. So changing the activation function will give you much better accuracy. Now we cannot be confused between 9 and 9, because still the same looks 9. This one looks 9. But if we will use the other one, maybe at some point it will be hard for us to differentiate between maybe 4 and 9. This one, at some point, maybe this one will look like 9. At some point, maybe this one will look like 0, 5, maybe 4, right? So we will lose some accuracy. So it's important to test the different types of activation functions. Yes. Autoencoder, we can use it for, sorry, if we will continue. Should we continue, or do you want to take some break? Should we just continue? Should we continue, or we just take a break? Because the next part will be denoising. We can use autoencoder for denoising. We can use it, in fact, for dimensionality. Yes, Ali? Okay, so we can take break 5 minutes or 10 minutes. Okay. So so next time we will start with denoising. How can we use autoencoder for denoising? Thank you very much.